I wanted to start with a little application here that I've used in some of my other classes to demonstrate the usefulness of what we're learning right now. This is actually supposed to demonstrate how if you have either a cell phone tower or a radio tower that is broadcasting a signal, how that signal gets from the tower to your home. And as you can see, what's happening here is you have an electron that is being vibrated in the broadcaster's antenna that is creating an electromagnetic wave which is traveling through the air to the antenna at the house, which is vibrating in sympathetic resonance, or just vibrating because of the energy coming through the antenna. And that is a wave. So your cell phones work this way, radio communication works this way, light fiber optic communication works this way. It's all basically based on waves. So what we're learning right now, the math of waves, leads you to being able to understand this a lot better. It's kind of a cool little simulation. If I change it to manual oscillation, I can actually control how to oscillate that electron. And you can kind of see it's not having much of an effect on the electron over there because I'm doing it too quickly, I think. Let's see if I can get that electron moving over there. Not much, if at all. So I'm not sure why it's not moving right now, but it should be. So anyway, I just thought I'd start with that little demonstration first. All right. We are going to be looking at graphing sinusoidal functions today. And before we do that, I kind of want to go through a little visualization exercise with you here, relating the graphs of sine, cosine, specifically, to the magic circle again. This magic circle is fantastic for being able to kind of understand how the graphs look, where do we start on the graphs, etc. So we're going to start by y equals sine theta. Okay, and we talked about the fact that the sine of the angle on the magic circle is the height of the triangle if I drop a line down here. So I'm going to do that for these first three triangles. And I want you to notice that this height keeps getting bigger and bigger in the first quadrant until it reaches this maximum height here. After that, the heights start to get smaller and smaller and smaller. And in fact, right at the beginning, what would be the height if I was on the x-axis? The height on the x-axis is 0. You have no height if you're on the x-axis. So the height starts at 0, gets bigger, 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 gets to a maximum, and then starts to get smaller, smaller, smaller to a minimum. And then it starts to increase in the negatives below. So these are supposed to be symmetrical here, folks. I don't quite have it drawn properly, but the height below, and I'm going to use a different color for that actually. The height below would be a negative height that gets bigger and bigger and bigger until it reaches a maximum negative height, and then it gets smaller and smaller and smaller until it gets back to 0. And that perfectly matches how the sine graph, the y values of the sine graph start at 0, go to a maximum, go back to 0, go to a minimum underneath at -1, and go back to 0. For the cosine values are a little bit harder to draw. They are the horizontal lengths along these triangles. So I want you to pretend that there's a dropped line here. I'm not going to draw it in because I want to concentrate on the horizontal lines, but how long is that horizontal line under this triangle? And I'm going to use another color. And then under this triangle, it's a little bit shorter. And then under this triangle, it's a little bit shorter. So going from red to green to purple, my cosine values are getting smaller and smaller. When I get to the 90-degree angle, there is no more length because it's gotten so short that it's 0. And I want you to also recognize, if I use black to represent the starting point is right here. Well, what's the length of the black line all the way to that dot? It starts at a length of 1 and then gets shorter, 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 all the way to 0. And I'm not going to draw it all the way around the circle for this one because I have a little thing to show you in a second. And then it gets bigger, 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 all the way up to -1. And then it gets smaller, 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 all the way back down to 0. So it's the heights for the sine graph and the horizontal lengths for the cosine graph. Now let's see if I can get this to work here. I want you to look at this demonstration. Now I'm going to have to wait for it to come back around, but what I'm going to do is I'm going to turn the sine animation on as soon as it reaches here, and I want you to see how the orange length, which is the height of the triangles in the circle, is being mimicked by this orange length drawing the graph over here. So these are the heights, which are the sine values of our triangles, and we are graphing their y value on the xy axis as the circle turns over and over again, or turns around over and over again. And that is how you generate a sine graph from the magic circle. Now if I turn that one on and turn on the cosine graph at that point, now the horizontal distance, look at how it gets bigger and bigger and bigger to a maximum size, smaller and smaller and smaller to a minimum size, bigger, bigger, bigger to a maximum size, and over again, starting with its maximum length at the 0 degrees, which would be a length of 1. Remember, these are radians, right? So pi over 3 is 3.14 divided by 3. So that's almost 1. And let's see if I can turn them both on at the exact same time. I'm going to turn that one off. And now you have both of them. So the green curve is the sine graph. The purple curve is the cosine graph. They look very, very similar to each other, but one of them starts big and goes downwards, which is the cosine graph. The sine graph starts at 0 and goes upwards. Notice that there's points where they cross. Look at this purple dot here is going to cross that green dot right there. I wonder if anybody can figure out why that's happening. Anyway, that animation is basically showing what I wanted you to see on the previous slides in an animated way. All right, let's go back to the note here. Okay, so the next step is what I want to do. I want to show you the parent functions and their tables of values for the sine graph, the cosine graph, and the tan graph. So we're heading towards transformations of graphs, which you've already started in some of the activities last week. But I want to really focus in on how to do this efficiently and quickly so that you could graph any trigonometric graph that you want. Now we will be seeing the tangent graph, but we're not going to be spending a lot of time with the tangent graph. You're going to see why in a few minutes. But let's start with the sine graph here. It's usually the one that people start with. And I'd also like to do it in radians to get you used to the rad values for these angles. These are the 5 key points we're going to use: 0, 90, 180, 270, and 360. If you, again, did the activity from last week, you would have seen those as the main angles, and you'll see why in a second. So that's 0 rad, pi over 2 for 90, and we're just adding pi over 2. So 1 pi over 2, 2 pi over 2 is just pi, 3 pi over 2 is 3 pi over 2, 4 pi over 2 is 2 pi. So those are your radian values for the angles. So whether we're in degrees or rads, we should be able to do this either way. So thinking of the sine graph, I'm going to go back to that magic circle picture for the sine graph here. The sine graph starts at a height of 0, because if you're on the x-axis, what is your height? Sine graph is heights on the magic circle. Your height is 0. So you start at 0. And now I want you to visualize that magic circle in your head. If we go 90 degrees, how high are we? We're at our maximum height, and the maximum height on a radius 1 circle is 1. At 180, if you can visualize that, that's at the same height as 0, which is 0. 270 is at the 6 o'clock point on a clock. That is at a maximum negative height of -1. And then at 360, we're back at 0, which is 0. So I'm going to separate my x-axis here by 90 degrees as evenly as I can. So we've got 90, 180, 270, 360, and it does actually continue. The graph is, unless we set a domain, it's going to continue on forever. So the next one would be 450, and it even continues on in the negative sides, which should be -90 degrees. Okay. And what I like to do on these graphs is I like to set myself some boundaries if I'm doing it on paper. And how I do that is I'll draw some dotted lines to show me how high and how low the graph goes. So the graph is going to go to a maximum height of 1 and a minimum height of -1. And if you draw those with a ruler on paper, it just helps you to see where your graph is stuck between. This would be basically the range of the graph, right? I'm just going to adjust that so it's a little bit more to scale. And now I'm going to plot the points. So we have 0, 0, 91, 180, 0, 270, -1, 360, 0, and then it would continue with the pattern on this side and on this side. So I want to connect all those points, but you're not supposed to connect them with straight lines. So here's what I like to do. Depending on how big this was on paper, it might be hard to draw the curves nicely. So I actually start with the curved parts at the top and the bottom of the hills, if you will. So I'm going to draw like a curve right here, and I'm going to aim that curve at those 2 points. I'm going to draw another one here. I'm going to draw another one here. And I'm going to draw another one here. And then I connect the points through those x-axis values, the roots of the graph. And I get a pretty decent representation of a sine graph. Okay? Now, I want you to understand that when we draw the sine graph, even though it does continue in both directions, that's what we consider to be kind of the starting point, if you will. It starts at 0, goes up, and then goes down through the x-axis to -1 and back up to 0. And then if we had to draw extra cycles of the graph, we would continue further on the left and on the right. So you need to memorize the x and y values of this graph, either memorize them or memorize how to develop them, how to come up with them, which is all based on the magic circle, right? For the cosine graph, let's do the same thing. So it's the same x values. Now the cosine graph at 0 degrees on the magic circle, that's the x length on the magic circle. So that is at a maximum, which is 1. And then at 90 degrees, that horizontal length gets really, really small to 0. And then it goes really, really big to -1 on the other side. And then at 270, small to 0. And then back to 360, which is there. So if I draw 90, 180, 270, 360. So this time I'm going to do in rads, just so that you see them written down. If I wanted to know the decimal values, I would actually put 3.14 in where pi is, but it's actually much nicer to do it with the fractions. I'm going to draw my 2 dotted lines again to give me my my range, so I know how high and how low I'm going to be going. So there's going to be 1, and right about here will be -1. And then I'll plot the points. So 0, 1 is my starting point, and then 90, 0, or pi over 2, 0, pi, -1, 3 pi over 2, 0, 2 pi, 1. Once again, at the top and at the bottom, I'm going to draw my little hills here. Nice little curve. And then I'll connect those lines through my the roots of the equation, and there is my cosine graph. So the sine graph, the cosine graph, hopefully that makes sense. And with the demonstrations that I showed you on the animation there, if you can visualize that magic circle, you should have no problems remembering all of those points. At least the 0, 90, 180, 270, 360. And then sine graphs start big. Sorry, sine graphs start at 0 and then move their way to a bigger value and then come back down to 0. Cosine graphs start big because they're the full x-axis value from 0 to 1. That gets smaller and smaller as you go up to 90 degrees, and then bigger and bigger as you go to 180 in the negative side. So I always remember it that the sine graph starts at 0 and goes up. The cosine graph starts at 1 and goes down. And then I can graph the rest of it from there. Now, what about the tangent graph? Let me just fill these in again. Now, the tangent graph is sine theta over cosine theta, which is something we saw a long time ago. So if we go to 0 degrees and look at the sine graph's value, the sine graph's value was 0. The cosine graph's value was 1. So this is 0 over 1. If we go to the 90 degree angle value for sine and cos, the sine value was 1. The cosine value is 0. That gives us an undefined value. This one was 0, right? 0 divided by 1 is 0, but 1 divided by 0 is undefined. For 180, the sine value is 0. The cosine value is negative 1. Well, 0 over negative 1 is just 0. And then for this one, we're going to have negative 1 and 0, which is going to be undefined. And then for 360, we're going to get 0 over 1 again, which is 0. So how do we deal with these undefined places on the tangent graph? Well, let's see. So let's go 90, 180, 270, 360. And we're going to put the negative 90 in there as well. So I have a point at 0, 0. Let me use another color for that, actually. I have a point at 0, 0. I have a point at 180, 0. I have a point at 360, 0. But I have undefined values at 90 and 270. Well, what that means, folks, is that we have asymptotes at those points. So at 90, I'm going to have to move it there because it's hard to place it perfectly. At 90, we have an asymptote. At 270, we have an asymptote. At negative 90, we're going to have an asymptote. So how does the graph behave? Now, I'm having trouble keeping things to scale, folks. This distance from negative 90 to 90 should be the exact same distance from 90 to 270. So it's not easy to do freehand. So let's go to Desmos again. And this time, we're going to go to this graph. So I've already typed in y is equal to tan x. I want you to see what y is equal to tan x is going to look like. So I'm just going to turn on the graph. And that's what y equals tan x looks like. So we have 0, 0, a point. Pi 0, remember pi is 180, right? But we have these asymptotes every 90 degrees. So that's what the graph is going to do. So you're going to have the graph start low, come up through 0, 0, and skim along each one of those asymptotes. It's not supposed to touch the asymptote, sorry about that. Okay, like that. And that's what the tangent graph looks like, and it's because the tangent graph is a division of sine divided by cos. So it is the only trig graph that does not look like a wave, and it does have its usefulnesses, but it isn't used very often in high school. So we will not be doing any transformations with the tangent graph this year, folks. I'll let future teachers show you those if you need them. But we will be doing transformations of the sine and cosine graphs. So with the transformations, remember that if you know your parent graph, you should be able to do any transformation from that parent graph. So let's start to look at that next. Before I do that, are there any significant problems in chat? Does anybody need me to re-explain something from anything we've done? Let me know. I'll give you a few seconds to answer. Okay, so we're going to talk about that right now. So there was a question in chat about what does the word amplitude, period, and phase shift mean? So that's part of what we're going to be doing today. I can do a quick little recap right away, in fact. So if I go back to the, let's go back to the sine graph here. So here's what amplitude means. Amplitude means how high from the axis of equilibrium does the graph go. Now, amplitude can actually be measured downwards as well, but it's an absolute value of whatever the number is, okay? So whether the number is 1 or the number is -1 in this case, the amplitude is just 1. So that's amplitude. Period is the horizontal length. So yes, good question in chat. It's from the middle of the graph, not from the x-axis. So because the graph can shift upwards or downwards, the middle of the graph isn't always the x-axis. So good question. It just happens to be the x-axis for like the regular parent graphs. For the period, it's the horizontal distance from the starting point of the graph to when the cycle ends and the graph starts to repeat itself in shape. So this point here is in the same phase as this point here. Phase meaning the same state. From that point, the graph goes upwards. From this point, the graph goes upwards. Those 2 points are in the same state. This point is at the same height as this point, so this one right here, but they are not in the same phase because the graph is going down after that point. So if you can find 2 points that are in the same phase from each other, one further on down the line, the distance between those 2 points is the period. Now the regular period for all sinusoidal graphs, cosine graphs and sine graphs, is 360 or 2 pi. Because that's the full circle, right? So your graph will repeat itself after the full circle. So that's what period means. Phase shift, I'm going to explain phase shift in a little bit, actually. So we'll hold off on that. You might already have an idea as to what it means. Okay, so I'm going to show you the transformations by starting with actually one of the most difficult ones. And the reason I'm doing that is because I am fairly confident that with all of the work we did with transformations of the 7 deadly curves early on in the course, that this should not be too much of a surprise. All right? So the first thing I want to remind you of is, what does the general equation look like? The general equation looks like this. Oops, sorry, I always mess that up. That's supposed to be a minus sign. And I'm changing the variables. I believe we used h and k for the horizontal transformation and the vertical transformation in the 7 deadly curves. For trigonometry, they almost exclusively, in most of the textbooks I've ever seen, use a k for the for this transformation for trig. So I specifically want to use k here, which means I can't use k at the end, so I'm using p and q instead. Okay? I'm hoping that this looks extremely familiar. Even though we haven't done it in a while, this is the general form of any transformation. So let's just recap what all of the different variables do. The a controls the vertical stretch or compress. If the absolute value of a is greater than 1, that is a stretch. If the absolute value of a is between 0 and 1, it is a compression. If a is negative, like it is here, that actually also means that the graph flips upside down. The k value is the exact same thing as the a value, except for the x's, and except for the fact that anything inside the bracket does the opposite of what you expect. So it's the exact opposite of a. If the absolute value of k is greater than 1, that's a compression. If the absolute value of k is between 0 and 1, it's a stretch. And if k is negative, that is also a reflection, but it's a horizontal reflection instead of a vertical one. P controls whether the graph moves left or right. Q controls whether the graph moves up or down. But P does the opposite of what the sign inside the bracket states. Now I want you to notice that the format of this equation is wrong. What do we need to do when we have a bracket like that defining the x transformations? Correct. We need to pull that 3 out. We need to factor that 3. Okay? So I'm going to do that right below here. And now we are in the proper format. Now we can see what all of the different variables represent. Now there's one thing in the activity, in one of the activities I gave last week, the question said, if P is positive, which way does the graph move? I think it was actually a C in the activity, but it doesn't matter what variables are used. I want to talk about that because it's a little bit confusing, and many students were making the same mistake. Can somebody tell me what is P as a number in that bracket? What value did I substitute in for P to end up with plus 30 in that bracket? Yes, but I want to know what let's say I asked you to substitute numbers into the equation to replace A, K, P, and Q. What number would you have substituted into P to get x plus 30 in that bracket? Ah. And this introduces a bit of a problem. And it may be a problem with the way that I personally presented this, but I'm trying to present it in a way that, in my opinion, after 23 years of teaching, is going to lead to the least amount of mistakes, okay? Which way does P equals negative 30 move the parabola? Or sorry, not the parabola, the graph. If P is equal to negative 30, which way does it move the graph? Be very careful here. Correct. This moves the graph to the left. Now I know what some of you are saying, but sir, you told me whatever the sign is, it does the opposite. Yes, the sign inside the bracket. Whatever the sign inside the bracket is, it does the opposite. But that's because if you pull the p-value out, the p-value is actually negative 30. I personally find this a little bit convoluted. I do find my way of teaching it is, in my opinion, better. I could be wrong on that. But if the question asks you, depending on the sign of p, which way does the graph move? If p is negative, it moves left, because when you plug it into the equation, it switches it to a plus. So just be a little bit careful the way teachers are asking that question. And, you know, if you need extra help on that, I may need to help you individually at some point. But I just wanted to point that out because on the activity, a lot of people were getting that question wrong. But it doesn't change the fact that what I taught is correct. If the plus sign is in the bracket, the graph moves left. I think I always tried to state that it was the sign in the bracket. Okay? All right. So let's do our transformations. And we're going to do all of these transformations at the same time. We're not doing them one at a time. I do not like that. I think it's a waste of time. If you have seen the transformations before, which you all did in grade 10, plus at the beginning of this year, you should be able to do this all in one step. Now, I am going to do 2 tables of values for this first one, just so that everything is as clear as possible. But we're going to eventually skip to just using 1 table of values. Okay? So the first thing I want you to look at is, what is the parent function? The parent function is cosine. We need to write the x and y values that we're going to use to draw our cosine graph. So our key points. Our key points are 0, 90, 180, 270, and 360 for the x values. And notice I left some room here, and I left the room there because there are x transformations that we're going to have to deal with. For the y values, cosine starts where? And right away, if you get this wrong, you're going to get the entire question wrong. All right? So correct. The cosine starts high at 1, then goes through 0, then goes to -1, then to 0, then to 1. All right? So I'm hoping that most of you are starting to be able to memorize that, either by looking at the magic circle in your mind or just having memorized the starting point. Let's do the x transformations first. So I'm going to use red to highlight the x transformations here. Let me erase those other lines. And I'm going to use red over here beside the x. So what does the k value do? It's a 3 multiplying the bracket, but we have to do the opposite. That means we have to divide by 3 all of the x values. And that's going to lead to a new thing that you have to know for trigonometric graphs. I could ask you, and I did ask you, to state the period of the graph. There is an equation for the period of the graph. The regular period is 360, but that is divided by your k value, because if your k value is 3, you are squishing your graph in horizontally by 3, which means your period is going to be less big. You're dividing your period into a smaller chunk. So 360 divided by k will be 360 divided by 3 in this case, which is 120 degrees. Now, had this been in rads, it would have been 2 pi over k, which is 2 pi over 3. Sorry, 2 pi over 3 as your period. All right? So this is a new formula that you now need to know. If I'm asking you to calculate the period of the graph, you take your k value, which is 3, and you do 360 divided by that, or if you were in rads, you would do 2 pi divided by that. So what does that mean? That means my graph will no longer go from 0 to 360. My graph is now going to go from 0 to 120 if it's not shifted. But the length between the starting point and the end point is going to be 120, okay, no matter what. You'll see what I mean when I graph it. Okay, so now we have to do the second part of our x transformations, which is the plus 30 in the bracket. But if it's plus 30 in the bracket, that's a minus 30 to the x values. Now we're going to do the y value transformations. The y value transformations are here and here. Let me use a different symbol for that, although I guess it won't matter. It doesn't matter because you'll probably be printing it off in black and white anyway. So -2 is multiplying as a y value transformation. That means it's multiplying our y values. -4 is subtracting. It doesn't change because it's a y transformation, so we subtract all of our y values by 4. And now what we're going to do is we're going to rewrite all of our x and y values with the new coordinates that we're going to use to plot this graph. Okay, so what is 0 divided by 3 minus 30? It's minus 30. What is 90 divided by 3? 30. 30 minus 30 is 0. 180 divided by 3 is 60. 60 minus 30 is 30. And now you can see that my graph is going up by 30s. So the next one's going to be 60 and then 90. Now, what is the spread of numbers from negative 30 to 90, it is 120, which is my period. So that all matches. Now we're going to do our y values. So 1 times negative 2 is negative 2. Negative 2 minus 4 is negative 6. 0 minus 4 is negative 4. 2 minus 4 is negative 2. 0 minus 4 is negative 4. And negative 2 minus 4 is negative 6. So there are all of my y values. And now I can sketch this graph. So one thing I want you to notice is the y values are highly negative, right? I'm going from negative 2 to negative 6. So that means I need a lot more room below my x-axis than I do above my x-axis. So I'm going to put my x and y-axis like that. And here's what I'm going to do. And this is going to come back this is going to go back to talking about something that was mentioned on one of the previous slides. My axis has changed. It's usually the x-axis, but my whole graph got shifted down by 4. So this is what I like to do when I'm graphing these on paper. I'm going to use a dotted line to show where my new axis is. And I know that because my graph shifted down by 4, that new axis is at negative 4. I'm also going to use the same dotted lines I used earlier to show how high does my graph go and how low does my graph go. Well, the maximum height of my graph is negative 2. I don't want to use the arrow one. Sorry about that. So right about in the middle here, that's the maximum my height will go. And then the minimum my height will go is negative 6. And those 3 new axes that I just drew there are going to help me plot the points that I need to plot. So let me just label them and label all of my separations here. So this is negative 2, this is negative 6, and I'm going to go up by the same x values that are in my x table here. So it's going up by 30s, right? So 30, 60, 90, 120, and negative 30 will be back here. Let's now plot our points. So negative 30 and negative 6 is going to go right here. 0 and negative 4 is going to go right here. 30 and negative 2 is going to go right here. 60 and negative 4, 90 and negative 6. And then if I had to continue, I could. Okay. And then I'm going to draw my little curve here, my little curve here, and my little curve there, and connect all those points. That one a little bit bigger. It's a little bit hard freehanding it, folks, but that's basically how that works. Now, I mean, like I said, I like to do all these transformations at once, especially after we've seen them all before. And I'm hoping that those of you who had learned how to do them step by step are starting to see the benefit of doing them all together. Sure, you might not see each transformation individually, but you should be able to visualize them now. And you can do all of this so much quicker if you do it all at once, I'm hoping. Now, we're not done, because I did ask to also list the amplitude and the phase shift. So what is the amplitude of my graph? Well, the amplitude is the distance from the new axis, negative 4, to the height of the graph that it goes to, which is negative 2. And I'm sure you can see that that's an amplitude of 2. But I didn't need to do the graph to do that. This is A. A stands for amplitude. Now, it's an absolute value, all right? So the amplitude is the absolute value of negative 2, which is 2 in this case. What is the phase shift? Phase shift in trigonometry graphs is just another word for horizontal translation. Okay. In fact, I've even heard the word phase shift used for horizontal translations in our other graphs sometimes as well. So how far did the graph shift over to the left or right? Well, again, we can look at the graph, or we can just look at the equation. Plus 30, oops, sorry about that. having trouble. There we go. Plus 30 means a left shift of 30 degrees. So 30 degrees to the left is our phase shift. And now we've finished that question. So I hope everything's starting to tie together at this point. I have two more of them that I would like to do with you, a slightly easier one and then a slightly more difficult one as well. So I'm going to switch slides if that's okay with everybody. Now, one little problem sometimes occurs when you give students less transformations to work with. So if I asked you to graph this, how would you go about doing that? Well, what are my only transformations? And where I'll get students that'll ask me for help sometimes is like, sir, how do I factor that? I gotta factor that, right? It's a number inside the bracket in front of x. It's got to be factored. Well, it's already factored. Those are two things that are multiplied. That's what factors are. So you don't have to worry about it. It's just a simple x transformation. You do have to remember that it's the opposite of what it looks like, though. So it's not a multiplication by 2. It's a division by 2. Okay. So, and now we should be able to start doing this all in one table instead of two tables. So let me draw out the table here. And it becomes an exercise, folks, in how fast can you do this without making mistakes, okay? So we've got x transformations, we've got y transformations. So let's set up our x transformations. So 0, 90, 180, 270, 360. Our parent graph is the sine graph this time. So that means our sine graph starts at 0, goes to 1, goes back to 0, down to -1, back to 0. And if you can visualize this shape for the sine graph, that should almost be enough to be able to figure out those y values. What are our x transformations going to do? Like I said, divide everything by 2. Our y transformations are going to multiply everything by 4. And if you leave enough room, you can put the answers right here. You don't have to create a new table of values. So 0 divided by 2 is 0, 90 divided by 2 is 45. It looks like we're going up by 45s, right? And does it make sense that if this is a 2, that is squishing my graph by 1/2 horizontally, which means my period is going from 360 to 180, right? So the period is 360 over k, which is 360 divided by 2, which is 180 degrees, and that matches exactly what we saw here. For our y values, we're going 0, 4, 0, -4, 0. What is my amplitude? My amplitude is 4 because I did not shift up or down, and from 0 to 4, the height is 4. That is my amplitude. There is 0 phase shift. And folks, I'm not going to graph this one. It's too easy. You should be able to do that. You'll be getting some practice to graph these anyway in homework. Let's not waste our time. Now that we got the coordinates, it'd be really easy to do. Okay, let's finish off with this one. As soon as you see pi or decimal numbers in this position, ugly decimals, that usually means that you're graphing in rads now. Okay? So that's the first thing I want you to notice. Second thing I want you to notice is this is not factored. Third thing I want you to notice is this is the cosine for our parent function. So let's factor this. How do I pull a 1/4 out of a pi? Well, you're dividing, right? You're going pi divided by 1/4. That's how factoring works. You're dividing out. So that's pi times 4/1, which is 4 pi. Okay, let's set up our table of values. Excuse me. I need a little bit of agua. Okay, so because we're doing things in rads, let's write out our x values in rads. So 0, pi over 2, that's 90 degrees, okay? And then we're adding pi over 2 plus pi over 2 plus pi over 2. So 2 pi over 2, which is pi, 3 pi over 2, which is 270, and 2 pi, which is 360. And then our y values are based on our parent function, which is a cosine again. All right, so the cosine starts high, so 1, 0, -1, 0, 1. So let's do our x transformations first. Our x transformations are this one and this one. So that 1/4 is the opposite. So multiply by 4. This minus 4 pi is a plus 4 pi. And I'm doing that all the way down. For my y value transformations, it is a 1/3. Now that's multiplying by 1/3. I just discussed this with the previous lesson as well. If you multiply by 1/3, I like to write that as dividing by 3. Okay, it's the same thing. So it's dividing by 3 all the way down. And then we're adding 1 to everything. So how quickly can you find the answer to each one of those and each one of these? Now, being a multiplying by 4 scenario, even though it's in rads, this actually works out quite nicely. 0 times 4 is 0. 0 plus 4 pi is 4 pi. Pi over 2 times 4, the 4's cancel out. With the 2, we're left with 2 pi plus 4 pi, which is 6 pi. And if you didn't follow that, write it out and see if you can cross out the 4 and the 2, and you'll see what I mean. Pi times 4 is just 4 pi. 4 pi plus 4 pi is 8 pi. And now you can see the pattern, right? We're just increasing by 2 each time. So, 10 pi and 12 pi. Now, if I asked you to calculate our period, what would it look like here? Because we're doing rads, we would do 2 pi over k. That would be 2 pi divided by 1/4, which is 2 pi times 4 over 1, which is 8 pi. And isn't the distance from 4 pi to 12 pi 8 pi? So everything matches. For our x values, 1 divided by 3 is 1/3. 1/3 plus 1 is 1/3 plus 3/3, which is 4/3. 0 plus 1 is 1. -1/3 plus 3/3 is 2/3. 0 plus 1 is 1. 1/3 plus 1 is 1/3 plus 3/3, which is 4/3. And once again, you can graph it from there. And that is the end of the lesson. It's up to you now to practice this until you are very comfortable with all of the terminology, all of the transformations. I can't show you an example of each one. In fact, I want to keep some of the harder ones for you to discover on your own anyway, and we can talk about them at another time. So, I am going to stop recording. I'll stay on stream for a few more seconds.